gentlemen, as we enter episode 12 of XPAD Live, we move away from concepts and confront the most important question of all. Can this system withstand real engineering validation? As Armour Harris makes clear, no military system is real until it survives rigorous technical verification. And that is where engineering validation begins. XPAD is not built on belief, but on data. The first step is aerodynamic testing. Extensive wind tunnel campaigns are conducted to validate stable transitions between horizontal and vertical flight, not in a single configuration, but across the entire flight envelope. At the same time, one critical challenge must be solved. Clean airflow into the engine inlet must be maintained throughout the transition maneuver. Failure here means failure of the entire VTOL concept. Next comes signature verification. XPAD is not designed for display, but it must survive in modern combat environments. Signature testing ensures the tailless airframe meets mission requirements. Then comes structural qualification. Test rigs are built to replicate real-world loads experienced during vertical launch, transition flight, and precision recovery. Every parameter must exceed safety margins. Assumptions are not allowed. Finally, the engine. Not just thrust, but throttle bandwidth required for vertical landing maneuvers. Thrust vectoring nozzles are integrated and tested on stands before any flight occurs. As Armour Harris emphasizes, this is not a parallel experiment chain, but a locked validation sequence. Each step must be confirmed before the next is allowed to proceed. This is how a real combat system is brought into existence.
How do we verify that XPAD can reliably transition between horizontal and vertical flight? How do we confirm that its structure can withstand loads, vibrations, and real combat conditions? How do we validate that the engine, thrust vectoring system, and flight controls have the bandwidth and reliability required for safe recovery? And most importantly, how do we transform a breakthrough design into real combat capability on schedule, at scale, and at cost? That is where episode 12 begins. In this episode, Armour Harris takes us beyond concepts and into the world of testing, validation, and engineering proof. From wind tunnel testing to aerodynamic verification. From structural qualification to engine testing. And from prototype to a roadmap toward real operational deployment. Episode 12 is not about belief, it is about evidence.
After posing the core question of episode 12, Armour Harris moves directly into the answer. Not with declarations, not with belief, but with engineering validation. The first step is aerodynamic testing. XPAD has undergone extensive wind tunnel testing to validate transitions between horizontal and vertical flight. The goal is not simply to demonstrate transition, but to ensure it is stable, repeatable, and maintains clean airflow into the engine inlet throughout the entire maneuver envelope. In parallel, structural validation is conducted. The XPAD airframe is subjected to tension, compression, and torsion tests, replicating real-world loads encountered during flight, vertical launch, and recovery under harsh conditions. The objective is clear: to prove the structure can not only fly, but survive in real combat environments. Next comes engine testing. The centrally mounted jet engine is tested for throttle bandwidth, response during mode transitions, and integration with the thrust vectoring system. This is a critical requirement to ensure XPAD can execute precise vertical landings with reliability. None of these tests occur in isolation. They are integrated into a continuous validation chain, where every data point feeds back into refining aerodynamics, structure, and control software. According to Armour Harris, this is how a modern combat system moves from design into reality. Not through a single leap, but through thousands of measurements, tests, and confirmations.
But engineering validation does not stop at individual components. What Armour Harris emphasizes is how these systems are tested as an integrated whole. Aerodynamics, structure, propulsion, and control software all must function together within a single operational chain, especially during the most dangerous phase, the transition from horizontal flight to vertical landing. Here, even small deviations can result in failure.
That is why the engineering team does not simply test whether a system works, but evaluates safety margins, error tolerance, and repeatability across hundreds of cycles. Alongside hardware validation is the verification of control software. Guidance, navigation, and thrust control algorithms are subjected to thousands of simulated scenarios, including conditions beyond human reaction capability. This is where XPAD fundamentally differs from previous VTOL designs. Not because it can fly vertically, but because it can autonomously manage the most complex flight phases without a pilot. Every step in the validation roadmap is designed to answer one core question. Can this system be deployed in real combat environments without relying on ideal conditions? That is why Armor Harris describes this not as testing, but as proving combat readiness.
After completing engineering validation, Armor Harris turns to the final element, the deployment roadmap. Not a vague vision, but a clearly defined timeline. The year 2026 marks the point when XPAD conducts its first vertical takeoff and landing flights. These are not demonstration flights. They are system verification flights. Engine performance, thrust control, transition dynamics, and autonomous landing stability. Each flight is designed to collect data, validate models, and gradually expand the operational envelope. From there, the system advances to the next phase. The year 2028 marks full mission-capable operations. This means more than flying. It means combat readiness. From launch to mission execution to recovery within a closed operational loop with a high degree of autonomy. Shield AI's objective is not slow experimentation, but rapid integration into mixed force structures as quickly as possible. Operating alongside manned platforms or independently, depending on mission requirements. As Armor Harris emphasizes, this is not about replacing humans, but about extending air power into environments where human endurance is limited. At this point, the overall picture becomes clear. XPAD is not a distant future concept. It is a system being validated, being tested, and steadily moving toward real-world deployment. From design to validation to deployment. That is the roadmap from theory to true strategic deterrence.
After everything we have analyzed, one thing is now unmistakably clear. XPAD is no longer an idea, no longer a drawing, no longer a promise. It is a system, validated through engineering, through testing, and through a concrete deployment roadmap. But once the technology is ready, the next critical question is always, how will it be used? In episode 13 of XPAD Live, we leave the laboratory and enter the battlefield. Armor Harris will take us deeper into operational concepts, how XPAD integrates into mixed forces, its role alongside manned aircraft, carrier strike groups, naval fleets, and modern combat networks. From a single platform to a component of national power architecture. If you found this analysis valuable, please like, subscribe, and enable notifications so you don't miss episode 13 of XPAD Live. I'm Hai. Thank you